Hello, this is Professor Neshiba, and I'm here to help you out with the items 3 and 4 of the handout, tuning a climate parameter and obtaining a climate sensitivity. So tuning a climate parameter, what that means is in the the isothermal atmospheric model, what we want to do is tune a parameter, in this case the emissivity or the absorptivity of the atmosphere, until we get a temperature at the surface, this value right here, that agrees with the observed mean value, which is 288 Kelvin. So you can kind of see here that with an emissivity of the atmosphere of 0.7, that we have a temperature that's too low. So you can play with this, and I'll just show you kind of how I might do it. Let's suppose I think that this value should go up, so I'm going to put 0.8 there for the emissivity. Then we go to the solver, and if you've already set this up, then everything should already be up, subject to the constraints and everything, so you can just solve again. And looks like I've done this, and let's just see what temperature it came up with. Now it came up with a temperature at the surface of 289.6, and now that's too high, so I presumably want to bring this down a little bit. So that's this item here, tuning a climate parameter. The next thing to do is obtaining a climate sensitivity, and the idea here is that if I change the albedo a little bit and see the resulting change in the temperature, I can see how sensitive the Earth's temperature is to that value. And just for reference, it's equation 8 here. It goes something like this. If I change the albedo by a little bit, it produces a change in the temperature. I want to solve for this quantity lambda right here. So we can do that, and now you'll want to do this for your optimal value of the emissivity, but for right now I'm just going to work as if that were the optimal value. So the albedo now is set at 0.3, and that's kind of how I've set up here. The albedo of 0.3, I just got a temperature at the surface of 289.6. We'll say that. Okay, so I'm going to say 289.6. And now the second value, 0.4, if you want to try that, go ahead and pause and try that. Okay, I'm just going to run it again, but put an albedo of 0.4 now, and of course run to the solver and solve and see what we get. And let's see, I got a temperature of 278.6, so I'm going to put this right here, 278.6, okay. And so now I've already kind of set up these next two values here. You can kind of see what it is. I've said the difference between those two albedo values is just the second value minus the third value, which of course is 0.1. And I've done the same thing here. I've said what's the temperature when we had the albedo of 0.4 minus the temperature when we had the albedo of 0.3. And that's number. So we got, when we increase the albedo, we lowered the temperature of the planet by 11 degrees. And lambda, going back here, lambda is obviously equal to that change in the temperature divided by the change in the albedo, those differences. So that would be that number divided by that number. I've already set that up here, C32 minus B32. And in this case, I get a lambda climate sensitivity parameter of minus 110 degrees Kelvin per albedo unit. And so that's what you'll want to be doing. You can do this in class on obtaining a climate sensitivity.